Hello, today we are going to be covering sections 1.3 and 1.4 possibly of your textbook regarding position and time and velocity. So let's begin with position and time. To understand motion, which is what we're studying in Physics 1, it's classical mechanics, we must quantify two main things. We must quantify position and time. I mean, if you think about it, anytime you have a task that you must complete. For example, today our students were talking about how this Saturday they're anxious because they're supposed to go take the SAT. Well, when SAT sends you your confirmation email that you're registered, you expect them to give you two pieces of information. They're supposed to tell you where you are assigned to take your test and when. Because if they only said, hey, you are signed up for 8 o'clock on Saturday, where in the world are you supposed to go if they don't tell you? Likewise, if they said, you have successfully registered for the SAT to be given at LTC, but they give you no date or time, when will you show up to make sure that you get there? Einstein considered this to be the fabric of space-time, kind of like you have an XY axis, and an XY axis would give you some coordinates like maybe 3, -2. So you know the 3 tells you that you go 3 spaces over in the positive x direction. The -2 says that you move down 2 on the x. To get to that particular point right there, you would need both of those pieces of information. Einstein said, life is like a giant grid of space and time, and in order for events to occur, you have to tell when you're supposed to be somewhere and where so that that can happen. All right, we are going to start off pretty simple with one-dimensional motion. One-dimensional motion is considered to be motion along a straight line. This would be like if you're walking down the hallway or a car driving down the road. It's real, actual motion, but in real life, most of the time we're dealing with two-dimensional, three-dimensional motion where objects are flying through the air or a golf ball being hit through the air and spiraling, and it gets more complicated, but we've got to start somewhere. So we are going to start by defining position today. Position in our case describes the location of an object at a particular time. Besides position, we are also going to need to identify an origin. Commonly, if we go back to our XY grid right here, you consider the origin to be this middle of the road where the X and the Y axis meet. Origin in our terms is very similar. Origin for us means a fixed reference point. A lot of times we define this as being the 0 point. You know, like in track and field, you have a starting line, and we would consider that to be point 0 or the origin, and everyone is supposed to run a set distance, like 100 meters, 200 meters from that point. This will help us to determine how far away an object is in its position. Next, we must also discuss the side or the direction of the position in relation to that origin. So are you positive or are you negative with respect to that origin? So let's say that we are dealing with a football field, perhaps. You've got all kinds of yard lines, but let's say that's the 50-yard line. And you're participating in a marching band show and you're trying to get your field show all together. If we say that this is your origin, and I say that you are assigned to march 10 yards away from the origin, well, that could be 10 yards to the right, 10 yards to the left, 10 yards up, 10 yards down. So that leaves it pretty ambiguous. How are we supposed to know which direction we go? All right, well, that is where we use positive and negative values to help us out. So in our case, typically, let me scroll back down, a positive value is a value that's to the right or upwards. Right in the cardinal directions is to the east, up is to the north. So a positive X value would be east, a positive Y value would be north. Negative is usually considered to be left or downwards. So you're talking about to the west or to the south. A west would be a negative X and a south would be a negative Y. All three of these things, the position, origin, and side or direction, are your three key pieces to describe position. So you need all of those. All right, so when we start talking about all this positive X, positive Y, negative Y, that gets us into the concept of a coordinate. Cartesian coordinates is usually what we stick to for the purposes of what you're used to. So a coordinate is a symbol that represents a position. And in the Cartesian coordinate system, you put X, comma, Y. So let's revisit the whole coordinate system. So this is generally considered to be the X-axis. This is considered to be the Y-axis. Let's change colors here and discuss. All right, so this side is considered to be the positive X-axis. This side over here would be the negative X-axis. This side is the positive Y, this side is the negative Y. In math class, you might have even seen these coordinates labeled as quadrant 1, quadrant 2, quadrant 3, and quadrant 4, which is all absolutely correct. But for our terms, we're focusing primarily on this. If you had a positive X and a positive Y value, that would mean that you are somewhere in quadrant 1 because you're along the X, positive X and the positive Y. If, on the other hand, you were given a value and it had a negative X value and a positive Y value, that would mean that you are in quadrant 2. If you had both a negative X and a negative Y value, you would be in quadrant 3. And if you had, let's see, choose orange here. If you had a positive X but a negative Y value, you would be in quadrant 4. Specifying these positives and negatives is going to help us tremendously in figuring out where your point is or your object is moving. Another really common way of expressing this is using east and west, north and south. So for example, if I gave you the coordinates -3, +5, I would go over here and I would go 3 units to the left on the x-axis, 1, 2, 3, 4, 5, something like that. 5 in the y direction, positive, and I get a point up here. Oops. Trying to figure out how to use this pencil very well. So your vector or your point would be pointing that way. And we would, in general cardinal direction terms, say that that vector ends up being pointed towards the northwest. All right. Another key component we said is not just space or position, but time. So let's discuss time. Time. A lot of times we will label something as T sub 0. T sub 0 is the time of origin, or the start time, the time an event is supposed to begin. There can be what is known as delta T. Delta T is the change in time. Sometimes we will refer to that as the elapsed time, or how much time has passed during an event. The delta symbol refers to change or difference in, and we will mathematically subtract if you're trying to find the change in something. So delta T is going to be equal to TF minus T sub O. Sometimes I'll write that as TF minus TI. Regardless, TF means your final time, so when the clock stops, and TI or TO is your initial or time of origin. So delta T, if you take TF minus TO or TI, is going to tell you how much time has passed, which is really important. Please remember, anytime you do a delta change in something, it is always final minus initial, never initial minus final. So there's not only a change in time, there can be a change in position, because we're talking about motion, moving. So change in position is referred to as displacement, which is a really, really, really important term for us. This is like our first big new physics term that we are going to learn. So displacement is given the symbol of delta X, change in position, because position is described as an X. And much like the time equation that we had, delta X is equal to XF minus XI. So delta X, we said, stands for displacement, how far an object has been displaced or moved. XF is the final position where that object was located, and X sub I is your initial position. So another very important concept for us to understand is the concept of vectors. A vector is a quantity with both magnitude and direction. So what's a vector in real life? Well, a vector could be something like displacement. If I needed to tell you where Oblong is in relation to Robinson, I couldn't just say that it's 8 miles, because it could be 8 miles in any direction. If you hopped in your car and drove 8 miles, you're not guaranteed to end up in Oblong. I would have to say that Oblong is 8 miles to the west of Robinson in order for you to correctly arrive there. Sometimes, in order to understand a concept, it's best to understand its opposite. So the opposite of something being a vector is something being a scalar. A scalar is a quantity with magnitude only. I coach track, and we do a lot of different running workouts that have lots of different goals. So sometimes I will send my runners out on a workout that says run for 20 minutes. I don't care at all what direction they go, what path they take. They can run circles, they can run down and back, they could run in a straight line. It doesn't matter. The goal of that workout is just to accumulate 20 minutes with your heart rate elevated. However, we also do some specific workouts that are on particular courses for a reason. For example, there might be a stretch of our cross-country course that has an uphill of 400 meters, and it's over halfway through the race, so it's pretty darn hard to make it up that hill. So we might practice that, and to do that best, we would actually go out to that portion of the cross-country course. We would start at the bottom of the hill and run up it for 400 meters and repeat that. The goal of that particular workout is a particular position and direction. It's not going to do me any good to run down that hill if in a race I'm going to have to run up that hill. So you have to put some thought into it. So that would be an example of like a vector workout versus a scalar workout. Sometimes you need both direction and magnitude. So for a vector, the first common example of a quantity that is a vector is displacement. because the displacement needs to know not only the magnitude of the change, but the difference in direction. So I actually should have written the equation for displacement as having a little line or a half arrow over the x to signify that it is a vector. For scalar, the I don't know, maybe sister quantity we want to say is distance. Distance is how far something travels. We give it a lowercase d, but it doesn't matter what direction you go. So that would be that workout, like go and run 2 miles, any direction you want to. We are going to do some practice problems here in the next couple of days about the differences between those. Let's see if we could come up with a problem like that. So a sample problem could be something like this. Let's say that you walk 5 meters east, 10 meters west, and then you turn around and decide you're going to go 20 meters back to the east. Like maybe you're trying to get to your neighbor's house, so you walked 5 meters to the east, realized that you forgot something up in your room that you needed to take with you, so you turn around and come back 10 meters to the west, and then you turn back around with the object you forgot and head to your neighbor's house. When we're dealing with these problems, it's really important to draw a graph. So I'm going to say this point right here is my origin. The first part of my motion was me moving 5 meters to the east, right there. But then I decided that I needed to go 10 meters the opposite direction. I'm going to call that a negative 10 meters because I was headed in the opposite direction. Finally, I turn back around and I go 20 meters total. Okay, now my drawing is not very to scale here, but let's call that XF because that's where I end up. All right, if I asked you how far you walked total, distance-wise, you went 5 meters in the beginning, plus 10 meters in the second part, plus 20 meters in the end, because distance, remember, doesn't care about direction. It's additive. You just add it all together. 5 plus 10 is 15. 15 plus 20 gives me 35 meters. Displacement is a totally different concept because displacement is a vector. And in this vector, you are supposed to take the x final minus the x initial. All it cares about is where are you at when you finish compared to where you started. Okay, so here is the deal. You walked 20 meters from here, right? And when you started that 20 meters, you were back here where you had forgotten, yes? All right, so if we really drew this out, let's think about it. You started here, you went 5 meters in the positive direction from your initial point, but then you went negative 10 meters. So negative 10 meters would actually mean that you end up back here negative 5 meters from where you began, because if you went 5 in the right direction and then 10 backwards, you're going to be 5 meters behind where you started. Then it says for the next part that you begin here at this point and you're going to go positive 20 meters. We can't say that we're 20 meters from the origin anymore. We can only say that we started at negative 5 and we went positive 20. So negative 5 plus 20 meters is going to mean I end up at a positive 15 meters from my origin. In this picture, the distance between where I started and where I finished is positive 15 meters. So perhaps a less confusing way to think about this, instead of using this equation for displacement would be for us to add all of these up, but pay attention to signs. So displacement in this case is going to be equal to positive 5 meters plus a negative 10 meters, because that was backwards, plus 20 meters in the correct direction. Will this give me the same answer I started with? Well, let's see. Positive 5 minus 10 will give us negative 5. Negative 5 plus 20 gives us a displacement of positive 15 meters for describing where we finish from where we start. Another classic example is, like, let's say that you run 1 lap around the track. So you start here, you run your lap, and you finish here. Well, you have run 400 meters because that's the distance around a track. Technically, your displacement, though, final position minus initial position, would be 0 because the initial and final are at the same spot. So that is a little loophole here that you must consider. When you finish where you start from, your displacement will always be 0. If you think about it, because displacement is supposed to be the difference between where you started and where you ended. Now, that definitely doesn't mean that you haven't gone anywhere. I mean, if you've run a 400 in your life, you know they're miserable and you can tell that you have run 400 meters. However, that's your distance. Your displacement is 0 because displacement says how far away are you when you finish from where you started. Don't let those problems trip you up. A roller coaster ride usually always has a displacement of 0 because you finish where you started. Tomorrow we will pick up with section 1.4 over velocity, which is another vector quantity. For today, just make sure you understand that in order to correctly describe motion, you must describe both position and time. And I hope you also understand the differences between scalars and vectors, and that distance is a scalar quantity.